So I'd like to take an opportunity to have a really honest look at the field, right? Why does the field even exist? Where are we going? Where are we at? So there are valid questions to ask at all levels of those statements. So to begin with, we're going to look at 5 generic approaches to quantum computing, because there isn't one, right? People look at lots of different things and are trying lots of different ways to do something interesting in the field of quantum stuff. So we'll have a look at each different way, its strengths and weaknesses, and and then I'll choose my favorite way and argue why it's the best. And then we'll go through what that means. So once you choose that way, what algorithms could you run on such a computer? How could you go about building such a device? How could you make sure that it actually works? And then the overhead of actually doing something that you can't already do with existing machines, and how believable that overhead is. So here's one generic approach to building a quantum computer. So you create an exotic state of matter, you excite some exotic particles, and you braid them around. Now, there are many beautiful features of this. It attracts a lot of high-grade, highly intelligent physicists. The biggest question mark is still, well, we haven't observed this state of matter conclusively. People are still debating the various experiments that claim to have demonstrated as to whether it's true or not, or some effect. It hasn't been reproduced, and we certainly haven't got to the stage of being able to store and manipulate data. Also, people have already identified some sources of noise and manufacturing defect. In some of these cases, these guys are near superconductors and they have quasiparticles, and that poisons the qubit and kills it. So some aspects appear to kill the robustness that the theory is intended to predict. So right now, I would say it's still an open theoretical problem, not just experimental, but an open theoretical problem as to whether these guys really will be robust, and in particular, exponentially more robust as you make all of the size scales of these devices bigger. So it's unknown, open problem. Here's another one. So we have a commercial quantum computer. You can buy one of these if you have a spare 15 million burning a hole in your back pocket. So it's an annealer, and what really that means is if you have some function of a binary nature, in this case anything up to 509 binary variables, it was supposed to be 512 but 3 of the qubits don't work, you can have a minimization of that function executed, worked out by this chip, and it does actually work. So you've got to give credit where credit's due. D-Wave has built a chip that does what it says it will do, and then all of the things that they get in trouble for are, just exactly how powerful that is, right? So it should be stressed that there's nothing a D-Wave machine can do that cannot be done classically. There are algorithms that will give you the answer for any D-Wave style machine, and indeed larger versions of the D-Wave machine. However, in some cases you can squint and argue the D-Wave machine might be sparse for specific instances if you massage the data in the right way. But nevertheless, it is a $15 million machine. If you throw $15 million of classical hardware at the same problem, you solve it quicker. Okay? They compare with single core or a small number of cores machines, which really, the big question is this: can you achieve commercially relevant performance, right? You can't sell someone a $15 million machine and say, yes, it really does solve these problems, but I could solve the same problem with a $15,000 workstation, right? So it is unknown if you can build a version of this big enough before temperature effects, which are known to be a limitation, decoherence effects, known to be a limitation, kick in and just stop you solving with any degree of acceptable reliability this problem. So again, there's still theoretical questions in addition to hardware. Yeah?
I'm surprised you're not emphasizing that it's not a universal, it makes no claim.
They don't make claim. It's this function that they minimize. This is actually a very useful thing classically. Okay? They don't need to claim it's universal because this is already useful enough. Yeah. Yeah, but minimizing of functions of this form is incredibly generic in the classical world. It applies to a huge range of optimization problems. This is good enough, right? The only question is, can you make it work cheap enough? And we don't know.
Is it theoretically a quantum?
It also doesn't actually matter. So people will undoubtedly argue until the end of time about whether it deserves to be called quantum or not. But fundamentally, the machine makes sense even if you view it as a classical machine, right? I mean, if you were going to say, I have a function that has some constraints, well, if you represent your qubits as loops of wire and the constraints as some particular interaction strength here, then if you just imagine the current in each direction as your 0 and 1, you can imagine the device settling to a solution of your problem. So really it then becomes a very grey question. To what extent is quantum mechanics helping me get there? And the fair answer that D-Wave will say is they don't care. They care that the device works, right? If you push them a bit harder, they will say things like, well, we believe, and again people debate, we've demonstrated 8-qubit entanglement. True or false, I don't know, but they will say that. And we believe, therefore, that we have 500 odd of these qubits, and every group of 8 qubits that is coupled can see tunnel barriers, and therefore there might be some advantage from quantum mechanics because groups of 8, of which there are many, of these can all see these little tunnel barriers and hopefully get to the solution quicker. Now that may or may not be true, but ultimately it only matters that the device works or not and can be built cheaply enough. So I have a lot of time for this approach. The theoretical questions are hard, open, but to me do not decrease the credibility of the device, which should judged be only by its ability to get answers. Now the D-Wave press, that's a completely another issue, but let's avoid that. So here's yet another one, boson sampling. Now here we're really not focused on really doing anything useful. It's about proving that you can play in the quantum world and get a speed up. However, again, we have this recurring issue, errors. It's unknown if errors will prevent this from being meaningful. See, it's a scaling argument. The claim is that as we scale this object, it's exponentially better. But as we scale this object, you have more and more errors, and sooner or later it doesn't work. So is that a fair claim? People are still debating whether that's a fair claim, or whether you can modify the claim to not have to rely on this hardware being perfect. Can you find some regime where even if these devices are imperfect, at the level you observe in experiments, that some aspect of the probability distribution you see here remains classically hard to simulate? This is unknown, all right? Valid question, but it's unknown. It's still theoretically not 100% sound, quite irrespective of the experimental challenges to implement it. Yet another one, quantum simulation. So you have some piece of physics you like, you build it in hardware, why not? Sounds like fun. But again, you really need to compare with classical techniques to see if there's any chance of a speed up. Now, to be fair to the people that do this kind of thing, they're usually not even looking for a speed up. But long term, right, if you want to be doing this in 20, 50 years and selling a device, it matters, right? You have to show that you can do something we can't already do. And it's completely unknown if you can build a sufficiently large-scale system, again with no error correction, that actually does something anyone cares about and would pay for better than an existing computer system. So there's still plenty of time to do that. In some ways, it's early days for quantum simulation, but we need a lot more people looking at what can be done classically to see if the engineering of these systems can be pushed far enough to do better. Or finally, you can do this, universal fault-tolerant quantum computation. And here I would argue our theory is done and has been done for over a decade. We know that if we can make a lot of qubits and get them working together to correct their own errors, then we can do arbitrary quantum computation. And so for this reason, because it's theoretically sound, because we know we can do it if we try hard enough, this is what I'm going to claim is the way to go, right? And that's what we're going to focus on in this talk. No, not the D-Wave, not quantum simulation, not boson sampling. The way, not D-Wave. No, the way. All right, so, all right, we can do anything with a quantum computer, but what does that really mean? So if you are in the military, secretly spying on this talk, that means you care about code breaking. So we have factoring, This was the first application for a quantum computer. We have ways of breaking the BlackBerry encryption, and even more exotic codes that people initially thought would be quantum secure. People are finding ways to break them, and no one knows the limits, all right? So there are plenty of proposals out there for more codes that are still, hopefully, quantum secure. They have some issues. The classical processing is higher, the key lengths are longer, but we really don't know how far you can push a quantum device as a code-breaking machine. And again, if you're in the government, you're already sold. You don't even keep reading. You say, right, I want one, build me one. But it should be stressed that this is not a commercial application, right? If you are IBM, you cannot pay for a code-breaking machine. It's illegal, right? You're not going to sit there and break banking transactions and Chinese communications. This is not a commercial thing. It's military. If you care about commercial applications, well, people say that 30% of worldwide superconductor time is spent doing quantum chemistry. Now, that number's a good start, but we really need to look at that number a lot more closely, because if quantum chemistry means molecular dynamics with 10 to 100 million atoms, if it means protein folding with tens of millions of atoms, this is not likely to be something that a quantum computer can help with, because the sheer representation of data already means so many qubits before you add in error correction that you're not going to build a machine that big, okay? We really need to check whether any significant fraction of that 30% is doing things like high energy quantum dynamics with small molecules, where you care about exactly how you catalyze a reaction or something like that, where the quantum effects might matter. You know, how do you build your porous platinum catalyst such that this product and that product go through at maximum rate, minimum energy, and all that kind of thing, right? These are the kind of quantum calculations you could imagine having an impact on. I don't know how much of worldwide supercomputer time is spent doing that, all right, versus protein folding, which is probably a lot, versus drug design, which might be a very large thing, which is probably a lot, and probably not amenable to a quantum computer helping at all. There are some other famous ones in exotic maths, so knot theory, calculating loop invariance of knots, again, exponentially fast. All the things I've listed on this page are exponentially faster than the best classical equivalents. Yeah? It is a random picture I got from Google image search. It represents the idea of doing quantum chemistry. Yeah.
Can you expand a little bit on why you think quantum computers would not be useful for protein folding, since that's something that
it's a data problem. Yeah, I know they claim. Well, people claim a lot of things without actually thinking about it. So, okay, let's think about it. How many atoms do you need to do a protein folding problem, right? You're typically looking at least hundreds of thousands to millions, sometimes a lot more. Some proteins are really big. So that means at the very least you need a bit per atom, and of course that's not enough. You're probably going to need 3 coordinates per atom, at least. So now we're talking about representing 3 coordinates. So let's keep it modest, say 16 bits per coordinate. It's probably, again, not enough. You probably need at least 32, okay? So if we take 32, you're looking at about 100 bits per atom, probably, as a minimum. And even if it's a really small protein, say 100,000 atoms, you're talking at least 10 million bits of information. Now, we still have no error correction thrown in. And as we'll see, error correction can blow up the overhead enormously. So even if I'm incredibly optimistic, that's going to be at least a factor of 10,000. All right, so we're now up to 100 billion qubits. That sounds really unfavorable. Okay, and that's a small protein with low precision coordinates, and assuming I don't need any extra information per atom. So it seems unlikely, yeah.
So your argument isn't based on that this is the kind of simulation problem where a quantum computer wouldn't offer an advantage, but rather just the practical concern about how big the quantum computer would be.
Yeah. It's pretty fundamental, yeah.
How large problems are being done classically?
So protein folding, you can do hundreds of thousands of atoms. Molecular dynamics, they routinely do up to 100 million atoms.
But obviously they also don't...
They're not very quantum.
Every atom. Well,
that's the point.
Not every atom.
It's done as a very classical thing.
Take the amino acids
Yeah.
as fixed things and then go from there.
But that's the whole point. People sit there and say, oh, we'll fold proteins. Protein folding is not that quantum a problem. It's a very classical problem, all right? We're going to design drugs. Most of that's all classical, right? How much quantumness is in your drugs? Not that much, right? So, you know, people make a lot of off-the-cuff statements, but when they do, they really should be picked up on them and said, give me a reference. What's your source? What are you talking about? But yeah, a quantum computer is not a high data device. You can't represent a lot of data in there. So if your problem natively requires a lattice of 1 billion atoms, probably, even if it's a quantum problem, it's completely intractable on a quantum computer. You'll never build a computer big enough just to represent the data before you even start talking about the computation. Yeah? So anyway, a lot of care is required to find problems of this nature that are actually useful and particularly commercially interesting. All right. So then you have all these exotic things which require a lot less overhead. But again, you've got to ask yourself who's going to pay for that. And then we're down to just speculation. So there's some things on machine learning where you take one object and say, you know, is it which one out of this class of objects? A very common problem. But again, it's pretty well solved classically. A lot of people work on it, not clear that we can give an advantage. And ultra speculative, if I put on wizard's hat, is, you know, maybe, just maybe, because artificial intelligence hasn't been solved despite lots of effort for a long time, a quantum computer is going to help us, okay? And that's about the level of which you should assign credibility to that statement. So the short answer is, there is no one application we have that is worth money, all right? So right now, if I go to an industrial giant and say, I'd like to build a quantum computer, I'm saying I want 5 to 10 million a year, growing exponentially as the computer gets bigger, for 20 to 30 years to build a device that will cost perhaps $100 million and has no known commercial applications. All right? That's where we're at. So we badly, badly need a lot more work on algorithms to identify something that would justify the cost of building the machine, right? Other than that, we're just hoping. And that's okay, I'm hopeful, but we should be very honest when we make that request for money that that's where we're at. So, keeping in mind that, you know, the dream of large-scale quantum computing, even if we realize it, is just something we hope will be helpful, let's nevertheless get on with trying to build one anyway, because it's fun. So at UCSB, we are looking at XMON qubits, and we have this little architecture which basically is this plus shape can be viewed as a capacitor, and the fact that it's neighboring this plus shape means it's capacitively coupled directly. These guys can be viewed as allowing us to tune the frequency of this guy, so there's also completely invisible some Josephson junctions that act as inductors, so this is a resonator, tunable frequency. And then you can tune these guys in and out of frequency without resonance with each other to execute gates. And it's quite a simple approach in terms of the number of objects on the chip, and it works quite well. So at the current point in time, we can demonstrate initialization, measurement, 2-qubit gates, all with better than 99% fidelity, and at the same time, identity single qubit gates with better than 3 nines. So this is clearly not a large-scale quantum computer yet. We need to have a 2D array of qubits at least. You know, you can't just have a chain of qubits. That's useless. If one of your qubits doesn't work, you have 2 computers, not one. So you need, for fault-tolerant reasons, if nothing else, you need a 2D array of qubits. We're optimistic, in collaboration with some people here at IQC, that the wiring can be moved to the 3rd dimension. We're optimistic that we can use microwave photons to communicate chip to chip. Hasn't been demonstrated, also hasn't been demonstrated the wiring in 3D, and optimistic that we can build a large 2D array of nearest neighbor coupled qubits, all with operations that includes the 2-qubit gate, better than 99.9% fidelity. So if you press me hard and say exactly how are you going to take this resonator, which is larger than this qubit, and put it in the 3rd dimension, I'll give the honest answer, we don't know. We're just optimistic that we can find a way to do it, all right? You know, it's a large architecture, but when your resonator is bigger than your qubit, that doesn't help you. It's likely that we'll probably need to put a bus of some kind between these qubits and then spread it out. So instead of being a simple 2D array with some questionable 3D wiring, you actually need a larger, so have a bus to create more space. And again, architectures of this nature are one of the reasons why I am physically here at this point in time, because Matteo Marantoni is working on, not exactly this, but something of this form where there's some more space and we can realistically hope to get the wires in. Here you can imagine now, well, sure, this guy is bigger than the qubit, but there's space for the resonator to go. There's space for contact pads. There's space to put a connector in. So again, you've got to do all of that and keep the fidelity high, but we're optimistic that we can do it. However, note that what I've drawn on the page is a bunch of qubits that interact only with their nearest neighbors. So we want to be able to control errors in a manner that is consistent with what we can build physically. And it's very fortunate that we have a wonderful code called the surface code that is completely compatible with that 2D array. So you only need nearest neighbor interactions, and you can get away with errors provided they're below about 1% per gate. So at the moment, the UCSB device, if we just allow ourselves to imagine we can build it in this manner, no buses in between, while preserving the current threshold error rates, the fidelities, and we try hard, so there are different frequencies for each qubit, and we have a look at a schedule that would actually work, and so on and so forth. So with just the assumption that we can magically control it, the physics stays the same, make it 2D, the numbers we currently have are at threshold, which means that if you improve anything, you start being able to correct the errors the device has natively. Now that's hard, don't get me wrong, right? Going to T2D, moving the wiring away and still maintaining performance and then making it even better is hard. We just believe we can. So we believe we can build a surface code quantum computer that will work, all right? Of course, the question is then, well, how big does it need to be to do anything interesting? So to answer that, you need to know how well the surface code works. And the answer is very well. So if we have a look at this bubble, what's it saying? It's saying, well, all these white dots are data qubits, and we are going to constrain those 4 data qubits to be in an eigenstate of the operator Z, 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 Z. We don't care which one, just we have to know which one. To work out which eigenstate we have, we use this circuit. We initialize one qubit, this is one physical qubit, interact it with its 4 nearest neighbors, and measure it. And that's a wonderful thing. So 6 gates, 8 gates if you don't allow yourself to initialize in the plus state and have to do a 0 and then a Hadamard, and same at the end, a Hadamard, then a measure in the Z basis. 6 to 8 gates gives you a classical bit of information. So not many things need to work to give you something you can use to stabilize your computation. Same deal for these guys. So the only difference between measuring a Z stabilizer and X stabilizer is instead of controlled Zs, these are controlled Xs, C0 gates. So you can implement all of these checks in parallel, and so you are very, very rapidly generating information that says, okay, where are my errors? Where are my errors? And then you can process it and keep bad errors, logical errors, chains of errors out of your computer. Because you need at least, this is the edge length if you like, in data qubits, D plus 1 on 2 errors to occur on some line before this thing can fail. So for example, if I had an error here and an error here, I would see a stabilizer value change here and believe that it is most likely that only one error occurred and that my error must have been here. And that will be wrong. When I put that correction in, it will complete a line. I'll have a physical error, software error, logical error, and I've lost my data. My computation's over. Yes? So everywhere you see an M is a qubit. So it's a uniform 2D array of qubits. Physically, they're all identical. Now, when I say that, practically you might choose, because you can't make them all identical, to optimize some things differently. For example, you don't really have to have a measurement device attached to all your data qubits. Physically, you might choose to only associate a measurement device with your measurement qubit. But nominally, at least at the theory level, it's just a uniform 2D array of qubits with nearest neighbor interactions. So how well does it work? So when you do these simulations, all right, so you go and code up a device like this, run it. You have single qubit, 2 qubit gates, depolarizing noise. So you execute a 2 qubit gate, you have a uniform chance of all the different tensor products of every different Pauli error. And then you go and identify where the errors are and process them, get rid of them. You can work out a probability that you have a logical error per round of error detection. So, you know, this is distance 3, which is this guy here. And then every time I increase the distance, I'm saying that instead of 3 data qubits on the edge, I have 5 or 7 or 9. So just bigger and bigger squares, all right? And you can look at this crossing point to work out the threshold error rate where it works. If you look at this point, you'll find a threshold error rate slightly below 0.6%. However, if you come far enough down, you notice that these lines are bendy, and the actual behavior well below threshold can be fit by this formula. 1 on this is 2%, so the code behaves well below threshold as if the threshold were 2%. And we believe this is about as far as you can squeeze things. We don't think it's going to get any better. You know, we've put a lot of years of work into the decoding algorithm. We've made it as efficient as it can humanly be. We're working on a proof that this is indeed optimal. And you know, we think we're done when it comes to classical processing, with the exception it needs to become a bunch of cold electronics one day, which will take years as well. But the algorithm itself, we feel, is done. So it works very well. So if you have a look here at our target error rate of 3 nines, right? Every time you increase the code distance, increase its ability to correct one more error, you get a suppression by over an order of magnitude, a factor of 20 indeed, okay? So even at just 3 nines, very modest target, increase the code distance, factor of 20 suppression in logical error. So very, very efficient code.
Should I read this as then you can get 10 to the 7 operations on average without a fault?
No, but we'll talk about that very shortly. Yeah. So to work out the number of operations you can get, you need to look a little deeper into the surface code. And while I'm not going to go through the details of this, let's imagine this is time, and not drawn in this picture is a great big 2D array of qubits, all right? Then you'll say, well, what on earth are all these 3D structures? These structures correspond to regions of space, time, where I turn off my qubits. I stop doing my checks there. And for the purposes of this talk, that's all we need to know. And so you can initialize a logical qubit using this kind of U-shaped region of space-time. You can measure a qubit by putting a crossbar on the top. And we have 2 different types of qubits, essentially corresponding to have I turned off Z stabilizers or have I turned off X stabilizers. And you can build up CNOT gates. I haven't drawn all the stuff that goes in the middle here. You can build a Hadamard gate in low space-time volume. And you can use this Hadamard gate to build S gates. So this gives us the full set of Clifford gates in low overhead. Now, unfortunately, that doesn't give you universal computation. You also need a T-gate. To get a T-gate, you need to distill an A state. This is 0 plus e to the I pi over 4, 1. And that's expensive. It's not too ridiculously bad. If you compare this to this, the volume of this is approximately 46 times the volume of this. So 1 T-gate is like 50 times more expensive than 1 CNOT gate. And if you've ever had a look at the details of just how much more powerful non-Clifford gates are to Clifford, that's not too bad. And we are, of course, still working on making this smaller. So working on compressing all of this structure further and further. We don't know what the limits are. I'm optimistic that we can bring it down a lot, but that will take time. Yeah?
What do the colors represent?
So up here, these colored bits represent essentially decoding my logical qubit to a single physical qubit and measuring it. So state distillation is an interesting process that can be viewed in the following manner. We want to prepare this state. All right. Now we can't do that directly. What we can do is there's a nice code. There's a 15-qubit Reed-Muller code. This code has a transversal T-gate. So if we had our logical qubit encoded like this, we'd actually be able to apply transversal T, and T is this, and get our desired state, A, which enables us to perform a logical T-gate on an arbitrary piece of logical data. So what you do is you start off with a plus state. I'm going to point to this region and say there's a plus state. You make it into a bell pair. So you do a C0. So essentially this bottom crossbar does that. So that gives us a bell pair. And that is basically this W shape is my bell pair right here. Then what you do is you take 1/2 of that bell pair and you make it a Reed-Muller thing. And that's what all of this does. All right? So that makes a surface code Reed-Muller logical qubit. So it's a logical Reed-Muller built out of surface code, all of this stuff. Once you've done that, you can apply error-prone T-gates. So you decode these bits. That's here. That's all of these tapering double pyramids, right? We're taking what used to be a nice big fat defect, which is well protected from errors, and shrinking it down to a single qubit. Then you just apply transversal T. Now this might at first case seem a little odd, but while these are error prone, we have error protection from our Reed-Muller code. So our Reed-Muller code is distance 3. That means it can correct a single error and detect any combination of 2 errors. And when you go through the maths, so we're only vulnerable to groups of 3 errors, right? Because if we detect an error, we discard the output. So you're only vulnerable to groups of 3 errors that are undetectable and corrupt the output. And surprisingly enough, despite the large value of 15 choose 3, there are only 35 combinations of 3 errors that both are undetectable and corrupt the output. So if we detect any errors here, we throw away this output. If we detect no errors, we keep the output. And our error rate P on these gates goes to 35p cubed. So we can produce very good T-gates and hence A states by doing this procedure twice in a row, because now this is order p to the 9th. So whatever error I started with down here, I'm going to have the 9th power of it plus some constant on the output. So you can achieve really, really robust gates.
So just so that I understand, the T-gate can't be applied in the logical qubit, but it can be applied to the physical qubit?
That's correct. Okay. Yeah. On a physical qubit, it's very easy to do anything. Yeah. There was another question, yeah? Kerry? Oh, same question. Good. So, those are the things we have to play with. Clifford and T-gates. That's what we can do. It's enough to do anything, but what are we going to do? So let's focus on something where there is, in my opinion, the strongest hope for a commercial application, namely quantum chemistry. We're going to start with something that is simple, calculating the ground state energy of a molecule. All right? This is surprisingly difficult to do if you want to do it with high accuracy, and indeed is currently, it scales exponentially, essentially in the number of degrees of freedom of your system, spin orbitals that you care about in your system. To do it on a quantum computer, what we're going to do is simulate the Hamiltonian of the molecule and look for the lowest eigenvalue of that Hamiltonian. So that's the ground state energy. And this can be imagined as, well, if I start with an atom that is shattered across the entire universe, nuclei and electrons, and then bring it together to form some kind of meaningful molecule, how much energy do I liberate in that process? This is the number we're calculating. Now, this number in isolation is completely useless because absolute energies have no meaning. But if you have a collection of molecules where you've done this, you can then work out how much energy you would liberate converting some into other products, okay? Now, of course, you could just burn the stuff and work out how much things heat up. So we're not yet really talking about something that is enormously useful, but this is still classically hard to do, okay? To really get to the point where someone would pay you a great deal of money to build a computer, I believe we need to go to dynamics. So as I said, I gave the example of looking at some slightly more complicated products as they go through a catalyst of some description. I think that might have some chance of being worth money. But this is still classically intractable, arguably not useful, but classically intractable, and it's physically interesting, so we'll look at this. Got to start somewhere. So the quantum circuit that corresponds to this calculation, the Hamiltonian. So this is one of the terms in the Hamiltonian on the previous page. I'll just flash it up again for a reminder. So we have a bunch of 2 spin orbital terms and a bunch of 4 spin orbital terms. And this is just one of those terms. There's a big sum over many of these, each one of which looks like this. So the key thing that you can barely see because of the blur is this is a controlled arbitrary angle rotation. So this angle depends on how many steps I divide my simulation into and the exact spin orbitals that I have. But just imagine it as an arbitrary angle. We know what they are when we begin our simulation, but they're nothing specific, right? Continuous angles. If you work out all of these circuits for all of the terms in the Hamiltonian, as has been done by the group at Microsoft, so you can thank Dave Wecker for these numbers, you get about 10 million of these controlled rotations per trotter step. So we're going to divide our Hamiltonian evolution into many individual steps. Per step, we have to do that many controlled rotations. Another area of very open research is really how many steps do we need to get to sufficient accuracy? Because sufficient is a complicated thing. Ultimately, it's a commercial question. What accuracy do I need, right? And people are still not sure. So the best I've been able to get out of people is that we need about 10,000. If you have any better numbers than that, I'd be very interested in it. So, but this is what we're going to work with. It's a reasonable number. It's supposed to get us to what's called chemical accuracy. And you know what we really want to know is what is commercial accuracy, and I don't know the answer to that. So this is the number, 7.4 by 10 to the 10 controlled rotations. Now, as we mentioned before, T gates are really expensive, C0 gates are really cheap. We need to look at how expensive a controlled rotation is to see what can be neglected, and a controlled rotation can be decomposed as 2 controlled swap gates and then a single qubit rotation. And you can decompose these into all of this circuit. Then you take your controlled rotation and you use some of the latest, greatest techniques on expressing these guys as sequences of HT. And you find that if we assume that errors in our rotations scale favorably, that is, if we have a small rotation angle that is in our system that corresponds to a probability of getting the wrong state that goes as the square of this. And intuitively, that should be the case. Here is the state I really wanted to rotate to. Here is the state I actually rotated to. If you imagine the overlap between psi prime and psi, that's going to go as epsilon squared. So this is the assumption we're going to make on our target accuracy using the latest techniques that decomposes into 51 of these T gates. So, you know, given a T gate is itself 50 times more expensive than a C0 gate, and for each controlled rotation, we need of order 50, in fact, of order 60 when you include these guys. So 3,000 of these C0s, basically. So a single controlled rotation is a good 3,000 times more expensive than a single controlled knot. That means that despite going back, there being of order 100 times more Clifford gates than these controlled rotations, these guys are still negligible. They're still of order a couple of % of the total algorithm. So all we're going to consider, all we need to consider, is the overhead of implementing these controlled rotations. Yeah? We will get to that.
Because you were saying that they take up a lot of space, and that's why they're important, right?
Yeah. When I say overhead, I always mean space-time overhead.
But in your circuit, your control rotations are all in the same, on the previous circuit.
Yep.
The control rotations are those ones on the bottom.
That's right.
There. So could you use the same gate again and again? Like the space would be confined because you just need to
Only if you want to do it very, very slowly. We'll talk about that.
Okay.
Yeah. So, temporal overhead, all right? So, one big question is, how long are these algorithms actually going to take to execute? And if you're not careful, the answer is an awfully long time. So this slide is about being careful. If you take an arbitrary algorithm, you can always decompose it as a layer of Clifford followed by a layer of T-gates. Clifford, T, Clifford, T. If you have such a decomposition, then you can always do this. You can take your first layer of Clifford, and then your first layer of T, and then do this teleportation circuit, which selectively patches in an S-gate correction for my T-gate or not, because all of the T-gates are probabilistically 50-50 T or T dagger. So I have to fix them as I go. And that's what this does. Based on this measurement, which tells me, did you get T or T dagger, I either patch in my S-gate correction or not. And I can then just teleport back sort of to the beginning of time and perform the next layer of my Clifford circuitry. Right here, T-gate, patch in S-gate correction. So the only thing that limits how fast any algorithm can run is this cascade of measurements. So I have to be able to perform a physical measurement, perform the classical processing to work out which logical measurement I got, and then choose to perform one of these two banks of measurements, which basically means either not doing a Hadamard gate or doing a Hadamard gate. So this is this 100 nanoseconds feed-forward single qubit gate time. We believe we can get to that. We can't do feed-forward at all at the moment, but we believe that's a reasonable number to achieve sometime in the next few years. So that means our execution time is a multiple of the sum of these two guys, measurement plus feed-forward. And that total number is, well, the number of controlled rotations. Then we have the number of T-gates per rotation, plus 2 to make it controlled, times this. And straight away, before we even work out how many qubits we need, we know that our algorithm must take at least 14 days. Now, this is an okay number. You can imagine someone waiting for some interesting problem for 14 days. This is not an uncommon duration to sit around staring at the wall. So what we now need, though, is the space overhead. So going back to Joseph's question, the question is, can you take the logical error rate per round of error detection of a square surface and equate that to the probability of error of a logical gate? And the answer is no, because there are lots and lots of these square surfaces, if you like, per logical gate. So we have to convert the data we have into something meaningful for this guy. So what we're going to do is take a worst case arrangement of these objects, which we call plumbing pieces. So we have a bunch of defects. We've got, a light and a dark. We've got primal and dual. They have lots of different names in the literature. It doesn't really matter. They're just two types of defects. So we're going to assume we have a forest of one type and interleaved with that same forest, which is not drawn, a forest of the opposite type. Okay? So two forests here. And then we want to upper bound the probability of error of every class of error. So we could have a chain of errors from here to here, or from here to here, and we can upper bound each one of those probabilities by the probability of error of a chain of errors from this boundary to this boundary, because this boundary and this boundary are longer than the face presented by this defect to this defect. So it's a good upper bound. Another good upper bound. Also, we have a ring encircling each defect. Again, there are very few rings that encircle a defect and match up with themselves. So again, we can upper bound that with a probability of error from one boundary to the other. So that's the 3 here. The 2 is for the 2 different types of defect. The 5D on 4 represents the fact that, well, we separate this length by D. So there are D rounds of error detection from here to here. that means this little cube is d on 4, and from here to here, the generic size scale of this whole picture is 5d on 4. That's here. And then we multiply by the logical error rate per round that we got in the previous slide. When you put that together, you get this nice little formula, and that gives you the probability of logical error per plumbing piece. And in this picture, if I imagine tiling CNOT gates, there would be, well, you can see 8 plumbing pieces. I would need another 4, so 12 plumbing pieces, to be able to tile this in 3D. So if I wanted to know the logical error of this CNOT gate, I would take this formula and multiply by 12. Okay, so that's how you go from square surfaces to the logical error of logical gates. Did that make sense, or was that complete nonsense?
Can I clarify?
Yes, please.
In the previous slides,
Yep.
the plumbing pieces were associated with single qubits in some sense, right?
No. So a plumbing piece is a great big construct of lots of qubits. So remember, this is the code distance, all right? And that's the temporal direction. This is also the code distance, and this is the spatial direction. In any spatial direction, the number of qubits is twice the code distance. So this is d equals 3, and you can see in each direction you have data measure, so twice as many qubits per d.
Okay, so this is like a cross-sectional picture of a single plumbing bit.
No, it's not even that. See, if I take a plumbing piece, let's see, this is a bigger picture. So this length from here to here is d, and so you could imagine this being just some patch of the computer, potentially between a square-shaped defect. One plumbing piece is just a 3D volume, all right? And it has a certain size scale. And what we actually simulate are square patches. So here's the 2-scale conversion between what we simulate. This is D, and the actual space-time volume of what we compute with. So if I take a concrete example, right? Let's imagine I choose this thing to be distance 3. All right, to be precise, there's going to be 5 qubits from here to here. It's a bit blurry, but if I went on the inside here, there'd be 5 from here to here. This distance from here to here is also 3, so this would be 3 rounds of error detection. Okay, so it's a space-time volume. Lots more than just one physical qubit. Each one of these is D here, D on 4 here, and so for a large code distance, this is a picture involving a large array of qubits for a large number of rounds of error detection. Yeah.
So, yeah, I didn't follow all the details. Maybe we could talk about it offline.
Sure.
Can you at least remind us what the definitions are of capital PL, lowercase pl?
Capital PL is on this slide, so this is the probability of a logical error anywhere in one plumbing piece. And let me perhaps draw a generic plumbing piece. So we want a 3D volume. And we want to be able to capture every possible object that we could have in that volume. So a plumbing piece contains the option for one of these cubic things in the corner, potentially one of these prisms in that direction, in this direction, and in this direction. They may not all be present, but there's the possibility. This one is, say, primal. And the option 4, also a dual one in the center. So again, all or none of these may actually be present, but we want to find a way to say, well, regardless of what's actually in a given plumbing piece, and of course these guys, if there's another one out the back here, there might be another dual plumbing piece here that feeds into it, right? So it's sort of an arbitrary 3D Microsoft screensaver style plumbing thing, right?
So what's your definition of a plumbing piece? Is it something?
This volume.
But is it the operations between error detection steps?
It's a volume. No, a definition of a plumbing piece is a volume that is big enough to hold a generic piece of the structure that does computation.
Space-time volume.
Yeah, it's a space-time volume. So we want to know the probability of logical error per space-time volume. Yeah? And what we have is the probability of logical error per round of error detection on a square of side length d. Yep. So we are working on software to get this directly. We don't have it yet. All we have is this. But we can use those squares, use that data in this manner to upper bound that. Yeah? Because the worst case scenario is you have two interleaved forests, one primal, one dual, of defects. That's where you have the most options for logical error. Yeah. Yeah, we're doing okay. We got 10 minutes. We're nearly there. All right, so space overhead. So we know how many T-gates we need. That's the number of controlled rotations, number of T-gates per rotation, plus 8 to make it controlled. It's 4 trillion of them. It's a lot. This is the gate error we're going to assume. So we're going to assume 10 to the minus 4. By the time you want to implement 4 trillion T-gates, I really hope that we're at 10 to the minus 4. So this means you need 2 levels of distillation. This structure, which corresponds to about 550 plumbing pieces. So we have 2 quadrillion plumbing pieces to implement. But fortunately, because the surface code works really well, particularly at this error rate, it only translates into distance 15. If we assume we have a 500 nanosecond surface code cycle, so this is this initialize 4 lots of interaction measure, right? So this is, again, commensurate with what we can do in the lab today. Then each plumbing piece with this code distance takes about 10 microseconds, and that means we can do about 10 to the 11 pieces in time in 14 days, which is the execution time we choose because it's the shortest possible execution time. That means that we need a factory producing these states involving at least 20,000 pieces in order to complete the necessary 2 quadrillion plumbing pieces in our available time measured in plumbing pieces. So that's the footprint size of the factory required to produce enough of these A states to satisfy the demand of our time optimal version of the algorithm. So what does that mean? We have D equal 15, 20,000 plumbing pieces. This is how we calculate the footprint of each plumbing piece. So, a data atom measure qubit times the edge length of your plumbing piece squared. It's about 1,400 qubits per piece, which is arguably a good number. I know it's way beyond what we can do now, but it's not 10 to the 20, right? It's 1,400. And that translates to 27 million qubits total. So again, you can take this one of 2 ways. You can be depressed and say that's an awful lot, and we only have 5 to 10 inside-the-art experiments. And then you can turn around and say, well, hang on, why? We only have 5 to 10 qubits in state-of-the-art experiments because there is no point scaling up yet. The qubits don't work well enough yet. We're only just now getting to the point, after 20 years of hard work, where the qubits have sufficient fidelity to even bother scaling up. And we shouldn't even bother scaling up until we get the qubits better. So it's reasonable that we still have a small number. Secondly, what do you expect? This is a classical computer, state-of-the-art, fastest in the world. It has 3 million cores and a petabyte of RAM. Right? If you want to outperform something that has 3 million cores, each of which has several 100 million transistors, okay? It is not unreasonable that you might need 27 million quantum bits. 27 million quantum bits, right? It's not really a lot to outperform it, do something that it could never do. Now, while I'm arguing this is already a good number, we know that there are ways to bring it down. People believe we can chop another order of magnitude off that. So we have all of these controlled rotations. If I have a rotation of angle theta, 1, and somewhere in the circuit, separated by some number of gates, there's some other rotation by angle theta 2. If I can work out a way to move these gates somewhere else, right? So that I can put these 2 together and get a single rotation, theta 1 plus theta 2, I just win. It's all win. I've got fewer gates, fewer rotations. I only need the same accuracy, in fact, less accuracy. So I have fewer total rotations. Each one, therefore, needs to be implemented with less accuracy, therefore fewer T-gates. So I can reduce strictly the volume of my algorithm without sacrificing anything. And people believe that you might be able to do this to save a factor of 10. Then we're talking less than 3 million qubits to outperform something with 3 million cores. That's a good number, all right? And who knows how much further we can go, but we shouldn't expect too much less. Anyway, to me this is an optimistic picture, but obviously challenging. You know, we're not going to have a quantum computer in 3 years or 5 years. We're not going to have several million qubits anytime soon. At UCSB, we're hoping to double the number of qubits every year from now because we feel the fidelity is high enough that that's worth trying to do. Yeah? Even if you do that, you're still looking at 20 years, 30 years to get to the kinds of numbers of qubits where we're going to start doing something classically interesting. So, to me, this is a very important statement. You know, we can't go to the public and say, oh yes, give me 5 qubits, give me 10 qubits, I'll outperform a classical computer. That's nonsense. People know it's nonsense. We can't even say, okay, it's a quantum chemistry algorithm. It has 112 spin orbitals. Therefore, it's an algorithm that requires 113 qubits. And when we have 113 qubits, we're going to outperform a classical computer. That's also nonsense. 113 qubits became 27 million when you add error correction. So, you know, we need to tell people that we need millions of qubits. This is the right thing to do because people need to be prepared to accept that it'll be 20 or 30 years before we have a quantum computer that'll do anything useful. It's just reality. But it's an okay reality. It's one I'm certainly okay with, one I think is reasonable, one I'm hopeful about. And we just need to accept the challenge, knuckle down and get on with it. Thanks.
Any questions?
Yeah, I see the problem with this 27 million, given the fact that the 10 by 10 millimeter chip can hold, let's say, 10 qubits. And yeah, going 3D stacking it, it would still be a 1 by 1 millimeter stack of silicium with thousands of layers to hold all those qubits. If we want them to still operate at linear frequency with this type of coupling and so on. So is that number compatible with the current way and the footprint of 1 qubit machine stacking?
How big is this machine?
Oh yeah, okay.
I think that's your answer. 1 by 1 by 1 meter would be an awesome outcome from my point of view. Yeah, that's small enough. I mean, if the computer fills this room, come on, seriously, that's fine. It's still much smaller than this machine. It's cheap. That's what we need. We need cheap qubits. We need to gun for $1 a qubit, right? So when you sit there and go and buy a $10,000 pulse generator to drive 1 qubit, you know, we need to question whether that's viable because one day we want it to be $1 per qubit. Ultimately, we need things like a superconducting qubit that requires only DC lines. For example, get rid of microwave control. It doesn't exist, maybe it can't exist, maybe it can exist, but we need people thinking about these problems, right? We need cold on-chip electronics that sit between our wires, like D-Wave does. Except D-Wave has a much simpler problem because they only have static control. They load a program and then everything runs. But whereas we need dynamic control, we need a chip that fits in maybe 1 by 1 centimeter that can actually drive a qubit. You know, people need to be thinking about this. That's the only way you'll get to a device that has any hope of being $1 a qubit. Yeah. Robert.
So Rainer Blatt often states as his research goal to keep a qubit alive, using quantum error correction to keep a qubit alive. I mean, in Santa Barbara, John Martini's group, do you have it on your roadmap?
Sure.
Sure. Can you give me a number of years? Say, are you planning to store a qubit through 100 or 1,000 error correction cycles? Do you have plans for
So of course it comes down to two things. How many qubits you have, what's your fidelity, right? So initially what we're gunning for is repetition code. So we're not going to try to go for full quantum preservation. It's too hard. So we're looking at 9 qubits, which are in the fridge now. And these, again, they all operate around the 99% level. And fortunately, this number is below threshold, significantly below threshold for the repetition code. So if you do sort of surface code analog, this should work. And we should be able to suppress environmental bit flip errors. Only bit flip, no phase coherence, but we should be able to show an extension of the T1 lifetime of a qubit. All right? And then maybe the year after that, we'll add another X qubits, keep it linear for the moment, and show that you get exponential suppression of error, which of course is a big open question. As you have more qubits, does it really work? Is something else going to come into play and stop you having independent errors and therefore exponential suppression? So that would be our starting point, because this is much cheaper to do.
It's all classical. that would be a
It's all classical, but it's out of quantum components. And yes, I completely concede it's all classical, but I hope people don't criticize us for being all classical. I think this is a very valid thing to do to see whether the 2D version could ever work. Yeah? And once we've done that, yeah, you have to start tackling the hard problems for going to 2D. And there are many, right? Wiring, crosstalk, temperature. As you start having a lot of control coming in here, you put a lot of heat load on your actual chip, and you've got to keep the temperature cold as you do this. And of course, all of that impacts ultimately on the only thing I care about, which is fidelity and whether it'll work. So we need to maintain high fidelities while making our life harder. So there are a lot of challenges, but yeah, if we can double the number of qubits every year, then we're working on 9 qubits now. In 3 years, that hopefully is 100 and is a 2D array, and we'll be stabilizing a logical qubit. That's ambitious, yeah, but we hope in 3 years that that's realistic.
Okay, that's an answer. Thanks.
Yeah.
Other questions?
Yeah.
Anyone thought about auto-tuning? I imagine we took
Yeah. So we're with. No, I mean even here, repetition code auto-tune is useful for this. So yes, yes we have an R, and yes is the answer. So it gives you better performance. So the threshold for the repetition is code is about 3% when you use auto-tune. Yeah. So yes, of course, yeah.
So you say John wants to reach like a 200 qubits in 3 years, so how is it going to be there in 1D?
No, in 2D is the hope. Yeah. But as I said right at the beginning of the slide, completely openly, there are no obvious solutions on how to do it. We're just optimistic we can. There are vague ideas. All right. Many problems that need to be solved to see how it should be done. Yeah. Yep.
You were saying that you don't know, it's not known how to implement a 3D architecture.
Not even 2D, so let alone, oh well, 3D with wiring in the top, no, it's not known.
Do you know any proposals?
No, oh well, yes, but no. Yeah. Not at UCSB, no. Yes.
Do you know D-Wave? Are they pursuing their annealing thing, or?
They're still building bigger and bigger chips, yeah. So they'll.
They're not branching out and trying something like that.
No, definitely not. No, that's fair enough. I mean, the device does actually work, so they're just going to push it, see how far they can push it, and see if it becomes commercially interesting. D-Wave technology is not in any way a stepping stone to a fault-tolerant architecture, but that's not their focus. It's okay.
When you mentioned the feed-forward instead of the physical level,
that means taking the measurement result, processing it slightly, and then using that result to control whether you do or do not do a single qubit gate. That's the feed-forward we want at the physical level. Oh, I think they have done it, but we have not done it, right? Yeah, no, I believe feed-forward's been done in a number of systems. Even optics, where it's really hard to do, they've done it, I believe. Yeah. No. So it won't be... Yeah, well, even in Super 90 may have been done. It's not done in UCSB. We need to be able to do it. That's the time scale we believe we can do it on. Yeah. Yeah.
Maybe I was asleep at the wrong moment, but did you ever tell us what Hamiltonian you needed to implement the service code?
You don't need a Hamiltonian at all. So, see, this is one of the big things about when you go fault-tolerant quantum computing. If you're not doing anything, the assumption is that these guys are non-interacting. So you bring these guys into resonance to affect controlled Z gates in our current hardware. And the Hamiltonian required to do this, frankly, is beyond me to write down and give a coherent talk on, because that's not really what I do. The guys at UCSB, every one of the other 20 members of the group, know that much better than I do. But you only have a meaningful Hamiltonian when you're doing something if your computer's working well. Now, of course, that's not true. You have crosstalk, you have environmental noise, and yes, you could write down a Hamiltonian that corresponds to our actual device. but our goal is to minimize all of that to make the evolution of a qubit when you're not doing something with it trivial and clean. So I couldn't give you an answer that I know would satisfy you, which is write down the actual Hamiltonian for the qubits we have, but I should stress that the surface code, the error correction, does not require a Hamiltonian. It requires gates, and that's something slightly different. It requires evolution, unitary operators, and I wouldn't personally say that this unitary operator, this 2-qubit operator, corresponds to a Hamiltonian. I would say it corresponds to a unitary. And I think that's a different thing, in my opinion. Yeah. We want to engineer our physical Hamiltonian to give us clean and controlled unitary evolution. And the surface code only calls for clean and controlled unitary evolution, not a Hamiltonian. Now, why that might seem not correct to you is many people do study the surface code as a Hamiltonian, all right, but that's not what we do. If you stick the Hamiltonian picture on the surface code, it's not robust. So if you require, 4 qubits and your Hamiltonian is this tensor product of x terms, right? And the neighboring one is this tensor product of z terms. This picture has been studied as a Hamiltonian picture, but it's no longer robust because as soon as you have an excitation, so say let's imagine this becomes an excitation, it can wander around without energy penalty. There's nothing forcing these things to go away. So this has been looked at and essentially it was concluded that it wouldn't work. All right? You have to do active repeated measurements of these guys, and then you want good, clean, controlled unitary evolution followed by measurement. And then, in my opinion, the fairest way to think about it is you no longer have a Hamiltonian. All right?
Yeah, you can say that basically it's called the state of the Doric code.
That's right. And you want to be able to evolve.
Just the state of it.
Yeah.
So because you measure basically this measure cube, so you project in one state of the Doric code. And in fact, as you said, I mean, if you want to do a quantum memory, that's what they call with the Hamiltonian, like with a physical device, it's thermally unstable in 2D. So you cannot do that. You actually cannot do it.
Yeah. Am I right in understanding that what you're saying is that the Hamiltonian is not gapped? That is gapped? It is gapped?
Is gapped, but the gap doesn't grow with size. Yeah?
I think there is quite some body of work.
Yeah, there's a lot of people that looked at this. Correct me if I'm wrong. The gap just doesn't grow with the system size, so there's no suppression of these excitations.
Okay. You need to go to 3D at least to make it stable.
Yeah, and even in 3D it works very poorly, and in 4D it works a bit better.
Or in ND.
Yeah, so direct Hamiltonian stabilization of quantum information, in my opinion, does not look very promising. We really need to have nice, clean gates and measurements and classical processing of that information to rapidly and efficiently remove entropy from our computer. Nature itself seems too lazy to do it.
I mean, I would go on with questions, but I guess people maybe want to go back to work. So let's go back.
I will stay here if you want to ask more questions, right? So I'll still be here.
Feel free to go to the cookies. That's it.